Bjarne and Andrew Sutton, who you haven't met yet, is actually Bjarne's postdoc. And they've been doing a lot of work in concepts being one of the things that didn't get into C++11. A lot of people were bummed out about that. But so now Bjarne is going to tell us what happened and what's going on.
Okay, I'm going to start. And halfway through, Andrew is going to take over. And then we'll both take questions afterwards. Basically, concepts is a mechanism that we were trying to get into C++ so that we would get constraint templates. Basically, so that we would know what a template expected of its arguments. And we're going to talk a little bit about that. First, I'll show the problem, what we would like to get done, what we have now. Then I'm going to talk a little bit, almost philosophically, about concepts. What are they? What should they be? And what went wrong? We worked very hard. We had a design, we had an implementation, but why wasn't it good enough? And then we'll show some experiments and a little bit about language design. If you want to read up on it, if you look at the slides, there are a technical report that we just submitted to the standards group. And there is a research paper that Andrew and I presented at a conference this year. You see there WG21. You type that into your browser, and you can get access to all of the Standards Committee's papers, more than you ever wanted to know about the standard. So the problem is, how do we express requirements on template arguments? This is very much work in progress. This is the last talk of this conference because it is the most speculative, quite researchy part of what might happen in the future. If you don't like research talks, you might not like this one, but you've been warned. So if you look at a template in the standard library as it is today, we can look at the code of a template like this, and we can see what does that code require of its arguments. What must a type be to be a good argument to fill? And we can look, there's a whole list of things. If we look carefully at the code and we experience, we can build up that list. And if we give the fill a type that doesn't meet that, well, we get an error, usually an obscure one. For the standard, we specify these requirements, and there's two kinds of requirements. What kind of operations are there, and what should those operations do? In other words, syntax and semantics. And a lot of the problem we're dealing with here is very simple, that compilers don't read requirements tables. We somehow have to tell the compiler what we mean instead of just do it. What we really have is duck typing at compile time. It happens late in the compilation process at instantiation time, and it reports in terms of uses and of types in the definition, and it requires a template definition. So let's look at fill there again. There are two examples. I call it with two integers, and the compiler, probably far too late for our taste, report that it can't dereference an int. Now, we may be able to deduce that that was because we passed an int where it wanted an input iterator, but that's not what the compiler says, because we never said we wanted a forward iterator. We're just using it, assuming it's a forward iterator. If we pass it a forward iterator like an int star, everything's fine. That's what we've got. What we would like would be to be able to say that we want a forward iterator. And not only that, we want a forward iterator, and we would want to be able to assign the value we're given to the value type of the forward iterator. And so if we make the mistake again, fill I, j of 9.9, it will say int is not a forward iterator. Just like type checking as we learned about it in kindergarten. Well, maybe middle school these days. And it's the other example is again okay. So that's half what we want. We want templates to have proper interfaces and proper type checking. And also, we would like to check our templates in isolation. It's hard to unit test templates because the template body has to be sort of married with its argument list and test whether it matches. And in some sense, we have to do that for all possible arguments. That's complicated. And the compiler knows better. Here we have an example. First becomes first plus 1, but for a forward iterator, that is not the case. So we should have written plus plus first. We will find that if we ever try to instantiate fill with a list, but if we don't, like only instantiate it with a vector, we'll never catch this potential error. It'll blow up next year in somebody else's code. And again, the standard says what's required, but the compiler doesn't know. So before we start fixing something, we have to make sure that we don't break anything that we really want, that we like. Templates are great for flexibility and for performance. So some people don't believe in the performance thing, but you know, templates don't generate any code for what you don't use. And also, it's really good at collecting information from a variety of places so that the compiler can get hold of it in one place and generate good code. And we can move work to compile time where it doesn't cost runtime. It's really good at exploiting inlining. In particular, no indirect function calls, no requirements of wrapping values into objects in a particular hierarchy, things like that. So we can get uncompromising performance in space and time when we know what we're doing. We don't want to compromise that. On the other hand, there's a lot of people who want to reason about template code. We heard about static analysis. We would like to have more static analysis, both on template codes and other template code. We want the types to be well behaved. And when we are talking about arguments to templates, we are really talking about types and requirements of types. The simplest form of that is types of types. And we need to be able to reason about that. So we would like to go there. Lots of people will go there. I think a lot of that will be external to the compiler, at least initially, till we understand what can be done cheaply, and what is useful to a lot of people. But we want it to be mathematically safe. Now here's a simpler statement of what we really want. Here's the first example. You know, a square root of double. Square root of 2 is fine, and square root of silly is not fine because it requires a double. So for a template that does a generic square root of a number, well, 2 is a number, so it works, and silly is not a number, so it does not work. This should be all we needed to know. Everybody can understand that. If you can understand the first sentence, you can understand the second. We want it that simple. The checking of concepts, of types and concept, which called concept, just has to be that simple so that everybody can use them. So what we want is a direct expression of our intent. We want to say that the intent is for this algorithm to take numbers, and for that algorithm to take pairs of forward iterators and things like that. And we want increased expressiveness. We want overloading to work really nicely and smooth. And we don't want to break existing template code. Okay, so we've got millions of lines of code out there using unconstrained templates. We want to impose a type system on it, and we want it all to work without changes, except in the cases where you had bugs. Now, I went to talk to a group of experts, and they said, well, you can't do that. I said, no, we did that. We want to do better now. So we can do this. And we want it to be relatively easy within existing compilers. Note the relative. This is not going to be trivial. Some people says, well, that's constraint genericity, fancy word. Eiffel, Java, and C# has it, and it's Haskell type classes. Well, it's not. It doesn't require a hierarchy. It cannot be implemented as a set of virtual function tables, set of indirect function calls, the way that's mostly done, because of the overhead that it would impose. We're using templates very intensely for performance critical situations, and if an abstract class is what you want, if the nice isolation of concerns that you get from an abstract class is what you want, you know where to find it. We've had them for 20 years. We want something else. We want to handle built-in types and user-defined types uniformly. We don't want wrapping to give overhead. We want to handle values and operations as arguments, and we want mixed mode operations. I mean, we don't want to go into all operations have to be of a single type. We really do want to be able to mix doubles and ints as we were used to. The C++ type system has to work with conversions and all the messiness that goes there. This is real world code. That's what we want. And getting that is not easy. And the reason we know it's not easy is that, well, a few of us has tried and failed, including the authors of this talk. So we want to back off and try and come up with something that is simpler, easier to describe, easier to implement, faster to compile, and prettier. So we're trying to back off, rethink the issue, and come back again. That's what we're doing. So our approach is, let's not design any language features for starters. Till we know what concepts are and what kind of concepts we would like, and how we would like to use them, how we would like to write them down from a user point of view, we shouldn't go and design language facilities. First figure out what we want, then figure out how to support it. That's the approach. And in the process, we have to understand the principles of concepts. What is it we're doing here? We're building a type system that is at a higher level than what we're used to. Our types is a type system for values. Here, concept is a type system for basically sets of types and values. That's non-trivial. And we want to formulate practical guidelines for design and use. If we can't have simple guidelines for how you use it, then we've failed, because we'll only get some small subset of the user population to use this. And I want everybody who can write a square root to be able to write a generic square root. I want everybody who can use a vector to implement a little vector-like abstraction if they need one. So basically everybody. Okay, what is a concept? If we go back and philosophical, the reason it's called a concept is that it's supposed to be a really general thing. It's something universal. Everybody knows what an integer is. An integer is what an integer is. The mathematicians have defined it. The concepts are stable, sometimes over centuries. There's a picture of Plato there, because if you're into philosophy, you'll think concepts are Platonic forms or something like that. Furthermore, concept tends to be idealized. It's what's common to a lot of things. An integer in math doesn't have a size. Integer arithmetic doesn't overflow. The C integer concept includes short and long and long and things like that. It's a generalization. It's an abstract version of what we've got. Very often, a concept is a fundamental concept of some branch of mathematics or computer science. All of the fields we deal with formalizing notions have concepts. They reflect about how we actually think about things. And every working generic program already has concepts. Remember, a concept is a set of requirements that an algorithm has on its argument types. The program ran, therefore somebody has thought through and thought about what was common for all the argument types that were presented. Your programs today have concepts. It's just they're implicit. The compiler doesn't know them, and you haven't stated them clearly. And you include me here, I'm not being rude. Even C has concepts. You look at it, there's integer types, there's floating point types. They are there already. We have to uncover them. So there's some examples here: natural numbers, integers, reals, functions, iterators of various sorts, lots of it. So let's see. To characterize an object, we have to describe how we can use objects of a type. All input operators, we have to be able to do increment to get the next one, and dereference. That's the syntactic part of it. That was the syntactic part in the tables, the left-hand side. Yes, left-hand side. And the semantics has to be described too. I mean, plus plus gets us to the next element, and equality also has to be exist there. I forgot to mention it, but basically, well, the semantic goes there. Let's not go further into the details at this stage. Basically, what is a concept? There's a picture of Alex Stefanov, who is the father of the STL and a major proponent of concepts, and a lot of what we say reflect his thoughts and his work. We worked with him for, well, in my case, for 20 years. Concepts are all about semantics. We have to do something, and it has to do the right thing. It's not just syntax. And furthermore, concept must be mathematically sound. Any random collection of constraints on a type doesn't make up a concept. It just makes up a mess of constraints that is unlikely to be general, to be mathematically sound, to have a well-defined semantics and all of these things. So that's the idea. And one thing that I think is a key operation is that operations comes in clusters. You can't, in general, write the semantics of an individual operation in isolation. I mean, what's the meaning of minus? If you have to give the semantic of minus and you're not allowed to say plus, you're in deep, deep trouble. Because, well, if you define plus and minus, they have to match. If you define star for dereferencing and the subscript operator, they have to somehow match. So one of the things that has to do with concepts is that you have to find a coherent set of operations that describe a concept. The mathematicians have done it for centuries: monoids, groups, real rings, field, vector spaces. And we have it for iterators. Stacks has push and pop. They have to match. So you're talking about something where a cluster, a group of operations has to match. And very rarely do we find a concept that describes a single operation. Addable is suspect. Subtractable is basically insane. So we have to avoid getting into this. And let's see, how does it use? Well, basically, we want to set requirements for the arguments, and there's a fairly natural syntax for an next. It takes an input iterator, next, so we say it's a template that takes an input iterator called iterator. Okay, again, how are they used? We express requirements on whole classes of algorithms. There's a sort, and of course, something that sort has to be sortable, that it takes an iterator and a relation, and the iterator and relation has to match so that the relation is actually something that's a predicate on the elements of the iterator. And so it all has to match, and we can put it out like that. And if you look at it, a concept is not really useful if it's only useful for one algorithm. Then it's very unlikely to be a real concept, to be something of generality and utility. Here, sortable is very useful because there's a whole bunch of sorting algorithms. They're listed there, and it also is the same notion that's required for binary heap algorithms and for the permutation generators. So concepts are general, useful, generic. They're not singletons by and large. Now, we worked on this actually very intensely for about 5 years for C++ OX. And this is something we came up with. That's not right. Whatever concepts are, we shouldn't have to say this. Has a sign? Is has a sign a concept? Not in my definition. Callable doesn't quite have any semantics. Copy constructible I can understand, but you know, the specification of that inner product is significantly larger than the implementation of inner product. There's something somewhat wrong here. And we need something simpler. So that's part of where we come from going through this philosophy. If you don't like the philosophy, look at this example. If you like it, you can take it. I won't have it. It's not good enough. And we get there by basically factoring things into the smallest parts. Think of a concept as a predicate on a type. Other predicates of the type is just asking which little properties the type has. And what happened was that we started with these large general concepts, and then we tried to figure out factoring it in all the independent parts. And we got more and more concepts. We got into language design too early. We were not emphasizing semantics, and we were emphasizing implementers of concepts and definers of library. We thought more about those than about the users of concepts. And finally, we didn't have C++11. There are features in C++11 that makes it easier to express this, notably template aliases and decal type. Andrew will get a little bit more to that. So basically, there's a concept design challenge. C++ OX had 130 concepts, plus minus a few. There's so many that it's hard to keep track of and count. That's absurd. There are not 130 fundamental concepts in the STL. How many do we have? About a dozen, I think. Maybe 2 dozen. Again, it depends on exactly what a concept is. We are trying to figure out what it means in the abstract, in general, for particular problems. So we worked on what is the minimum number needed to specify it? What is a convenient number? Because maybe the minimum becomes too messy and we need a little bit of convenience and summary kind of thing. That's what we found. So we'll work on it. So one thing we got was, let's look at it. A concept is a set of syntactic constraints plus some axioms specifying the required semantics. Now, before you get the wrong idea, an axiom in math is something you don't prove. We're not going to try and verify the semantics of the various concepts, because usually we can't. It's not available. The axioms are very useful for generating test cases, but it's not a testable thing. We can check whether something has the syntax, but we are asserting that something has the axioms. And so we make this distinction because we found it useful in design, because we think it is a fundamental distinction in the way we think about concepts well. The word is well chosen, so well that it becomes hard to distinguish between when I'm talking about the technical meaning of axiom and the conventional meaning of axioms. So let's look at one of the things that are at the basis of a lot of our thinking. It's a notion of regularity. If we don't have regularity, it's hard to think about it. A regular type is a type that sort of behaves a bit like an integer. We can assign them, we can copy them, we can take their address, we can compare them for equality. Some of them has an order, so that will mean they're ordered in addition to be regular. In C++, we can construct a lot of things that aren't regular. Like we can make types that you can't take the address of. You can make type you can't compare. That's easy. You can make type that you can move but not copy. That's very rare. Anyway, regularity is the foundation of a lot of what we are doing. And if you look at the STL, essentially everything requires regular types. So here we have sort of the prototype of a modern concept. We'll go into that. When we design concept, there's a spectrum. We can take ad hoc requirement, just find anything we like, or we can abstract. and make abstract concepts. We're looking for a sweet spot in this thing, but we are definitely biased towards the abstract concepts, meant to be more general, meant to be more regular. The ad hoc is for things we don't quite understand yet. Now, the principles of concept design, as articulated here, came to a large extent out of a meeting in Palo Alto in August, called by Andrew Lumsdaine from Indiana University, hosted by Alex Stefanoff. Alex is the guy to the left here. His colleague Paul McJones, that has done a lot of this work there, is to the other side. The guy in the middle invented functional programming and Fortran, and he wasn't there. He's not part of this. Anyway, the principle is we want to emphasize the distinction between universal and ad hoc requirements and focus on the universal. We want to see concepts an idealized and consistent set of properties. We want to raise the importance of semantics in our conceptual specifications. You look at the standard library, there's a syntax requirement, and then there's a semantic specification, and there's the precondition, postcondition. It's been growing steadily more formal. We want to capture that, and we want to have it mathematically sound to support equatorial reasoning. There's been several efforts. Our effort was started at that meeting. The low guy there is Andrew, the smiley guy. No, they're both smiley. The other one is Sean Parent from Adobe. So those of you who know the history of concepts in C++ OX know there was an Indiana proposal, there was a Texas proposal, and there was an incomplete compromise. We're all there together with a bunch of Californians. Okay, so we ended up with this. These are all of the concepts that we came up with for characterizing the standard library and a bit more. Same, derived, convertible, common, function, regular function, predicate, relation. You've heard all of these words before. I mean, they are, after all, the concepts we use to describe the standard library. And they fit on a slide. That's very, very important. We can and we will have great arguments about the details of the individual concepts here, and whether we need one or two or something. But the point is, we've reached the point where we can talk about it on one slide. And it makes sense. There is a 130-page report on this whole work that you can go and look up. And it'll mutate further, but it's fundamentally much simpler than what we've seen before. There's 34 concepts. About a third of them are sort of general concepts that you could actually live without, but it's more convenient to have them. Well, let's not go into details here. So the way it will look is something like this. Here we have one of the new algorithms in the standard library, ORLOF. It takes a sequence defined as a pair of iterators, and these iterators are supposed to be input iterators, it says so, and that requires that you can have a predicate that's a predicate over the value type of the iterators. That's fairly straightforward. This is actually simply a syntax for saying what you would be doing when you described it. And we can shorten it a bit. Look at the lower bit there. We want an input iterator, which we call iter, and we want a predicate of its value types, and a predicate of the value type. So a predicate is something that compares two values of the same type, and we call that pred. So that's pretty nice as a way of expressing things, and we can do that. Notice, by the way, that the predicate doesn't have any of the colon value or colon type kind of stuff. We don't need that. This is C++ 11. We can do it even without language extensions. Find, which you've seen, it takes an iterator, and you want equality to compare the value type, And okay, that's the version that's uniform. And find if is the one that takes a predicate. And at this point, I think I should give Andrew his half hour. He can talk about the language part of it.
It's my turn now?
Yep.
Can you guys hear me? This on? Okay, great. All right, so hopefully Bjørn has given you guys a good description of the problem we're trying to solve and the approach that we're taking to do it. My job is to tell you what we actually did. So this is pretty much going to be a discussion of, or description of, what the language that we used, the language that we actually use to describe concepts. So a concept in our view is really just a predicate. That's all it is. It's a predicate. You use it to evaluate properties of a type. So returns true or returns false. So for example, if we want to ask if an integer pointer, int star, is an input iterator, we would write what you see right below that first line there. Input iterator int star. And this actually evaluates, or should evaluate, to either true or false, depending on whether or not int star is an input iterator. And I assure you that it is. So the concept actually just evaluates valid expressions. We want to look for the syntax that we've said it was going to work with and determine if we can actually resolve that against the type. We can also look up associated types and determine whether or not those are valid too. But those don't actually occur as often as we think, or as often as we used to think, I should say. We can also associate semantics with concepts. And semantics in our case are pretty much just axioms. They're rules that describe how that type behaves. And I'll give you some examples of these a little bit later. But for the most part, we're going to talk about syntactic requirements. I will mention one thing. Axioms are mostly part of the documentation. We're not requiring the compiler to actually do anything with them except to verify that it's valid C++. We're not proposing to do any, we're not requiring the compiler to do any model checking or theorem proving based on these axioms. They're primarily there for documentation at this point. We hope that's going to change in the future. So a concept looks like a predicate. It looks about like this. It is a predicate. We start with concept, then we have the concept name, and then the parameters that the concept is evaluating, usually type names. This isn't always the case. We can certainly use non-type parameters also. Unlike C++ OX concepts, our definition has an equal sign instead of an open brace. Concepts don't introduce scope in this model. The only thing they do is answer yes or no. We can't associate types through them. Concepts are conjunctions. So you can see here we have a concept defined that takes two other concepts, semi-regular and equality comparable. And we expect that to either be true or false also. When you actually go through and define requirements, we introduce those with a requires clause, which works just like this does. So a requires clause can be parameterized over objects. Here, two objects of type T called A and B. We use these to help write valid expressions. What's inside that block is it's several things actually. The A equals B part is a use pattern. It says how we expect to use the types, use type T or the objects A and B in this expression. The bool with the initializer braces there describes a constraint on the result type. What we're saying is that A equals B must be valid syntax, and the result of that operation must be explicitly convertible to bool, or I think technically contextually convertible in some cases also. If statements, while loops, things like that. That weird syntax for describing result constraints actually has this as the rest of it. So we kind of borrowed the initializer syntax and made some small changes in order to describe result types. So the first one, bool x equals y, that says that x and y the result of that expression has to be explicitly converted to bool. The second one says that star I must be implicitly convertible to a constant reference to type T, which is kind of a strange thing to say. Basically, it says you can bind a constant reference to the result of that expression in this case. But the equal sign means implicit conversion, usually. And the last one is the result of I or plus I has to be the same as reference to I. So the equal here is a sort of an extension of the declaration syntax to get same type constraints. The actual meaning of the last one is given in the comments. So same decal type plus I. that's either true or false. So not only do we have the syntactic requirement, we also have another concept applied to the result of that argument, which it turns out you can always do using decal type. A very nice feature to have for concepts. Axioms look about like this. You introduce them with an axiom block. This one is not parameterized, but just like a requires block, you can introduce new variables to quantify an axiom over. So here these are the semantics of an equivalence relation. So we have the first one is reflexivity, and then symmetry, and then the last one is transitivity. These primarily just document how that expression is required to behave in your programs. If you write an equal operator that doesn't satisfy these requirements, the semantic requirements, you've probably done something wrong. And I think some algorithms that require equivalence or equality won't work quite the way that you think they do. Oh yeah, we've also introduced a couple new operators here. The implication operator for the symmetric or symmetry requirement, and the equivalence operator, if and only if. The equivalence operator is a change from some set of proposals from C++ OX by Gabby Dos-Reis. This was known as behavioral equivalence then. We have it as if and only if for the time being. I think we might be going back to behavioral equivalence in the near future. So, okay, so the entire equality comparable concept looks like this when you put it all together. Notice that we're not just requiring the equality operator. We also require not equals. But as Bjarne said, concepts come in clusters of useful operations or related operations. It doesn't make sense to require equals, but not its inverse. There's negation. So we actually require both of these. We're not actually providing a definition of not equals either. This is just a requirement. This doesn't introduce any new declarations that you can use in generic algorithms. Purely requirements. Associated types. So this is our weakly incrementable concept, which I think is mostly around for backwards compatibility with C++ 98. We introduce an associated type requirement using template alias, usually a template alias. So here we're saying there's a type called distance type of I. There's a type named by the alias distance type. It takes I, the iterator, as a parameter. If that alias doesn't resolve to something useful, then the concept cannot be valid or fails. It's false. So if there's not an associated distance type with I, then the concept is not going to be true. We can also use concepts to further constrain these things. So we require that the distance type is integral. So must be a built-in signed or unsigned integer type, like long or size t here. And let's see, anything else? Oh, OK, so no, that's it. That's concepts. That's how you define concepts. That's it. There is nothing more to it. I think if we were giving this talk 4 or 5 years ago, we could probably spend the entire hour talking about how you might actually define concepts and how they're used. I think we can do it in 4 slides in this case. If you really want the full range of syntax, you should go look at in3351, which is the technical report for WG21. I think these 4 slides have covered everything that we've actually used in that report. So the last part of my talk, I guess, the last part of this talk, really is about how we're using these or to constrain the STL or some other features associated with these. Well, to start with, we don't have traits classes anymore. They're gone. So if you got tired of writing standard iterator traits, iter : distance type or difference type or value type, you don't have to anymore. This is gone. We just replaced that with the required distance type alias. So here's the distance algorithm. The reason that we actually prefer this is that distance type now becomes part of the interface of the iterator. We can completely separate it from its implementation. So it doesn't matter to us how the actual type gets resolved. You know, we have a built-in somewhere for pointers, which is probably going to be pointer diff t. Or you can have a nested type name for most custom iterator classes. But generally, we don't care. Concepts are about the interface, not about how you actually get those things to the right place at the right time. So iterator traits, if it does exist, actually becomes entirely invisible to how you write generic libraries now. If you really want to know why it's called distance type and not difference type, you should ask me later. There's a good story on that. Oh yeah, we can also overload based on concepts. I know this was a feature that was quite heavily cited as being important from C++ OX. We think this is still an important feature. So for example, we can overload distance for input iterators, which counts individually until you reach the last element. Or for random access iterators, you just subtract and you get the right value. Notice I didn't actually say anything about refinement. I know if you guys were reading the C++ OX, there was explicit syntax to refine one concept from another. We don't need that. We just look at the set of syntactic requirements and choose the one that's the most specialized, which just becomes a subset problem. So we can actually figure out, okay, well, an input iterator has this set of requirements. Random access iterator has those, plus more, plus equals, plus minus, subscripting. And we can just pick based on that. And there's no other work that you actually have to do there. We do still run into issues where there are semantic differences between concepts, but not syntactic differences. And the prime example of this, or the prime motivating example for this, is input iterators and forward iterators. So an input iterator, you can move forward, but you really can't have multiple iterators into the same stream at the same time, because when you increment one, you've probably just invalidated the data being pointed at by the other one. Forward iterator has the same interface. You can increment and dereference, but you're allowed to have multiple iterators into the same stream. So think about a vector. You have 2 pointers. If you increment one, your data is still going to stick around. Also called the multipass property. So can we overload these functions? And the answer is yes, but we are going to actually have to do a little bit more work. And this is kind of the one place where we sort of stuck with the C++ 98 way of doing things, a little bit. Instead of, I'm sorry. Now, basically we're using the same iterator category trick here. So we're looking to see if the iterator category for some type is actually derived from input iterator, forward iterator. And this actually becomes a static check now, because we can determine whether one type is derived from another at compile time. You know, it's an initial pass. We hope to improve this. It'd be great if we could actually get rid of the need for iterator categories altogether, I think. But we're still working on that one. Actually, you don't really need iterator category anymore. You can kind of get rid of the entire iterator category property and just go with a single property for multipass and do something very similar to this. But we have iterator category as a holdover. Notice the only thing left for forward iterators are the multipass requirements, just semantics. So the last thing that we actually did when we were using these concepts is we found that it was really useful to group algorithms into families. And this isn't terribly surprising. If you actually look at the standard, it does that for you. But in a lot of cases, what we find is that the requirements for all these concepts are basically all the same. So for example, Bjarne mentioned sort before, and we had a bunch of sorting algorithms. Well, all of these algorithms here, sort, partial sort, stable sort, nth element, those guys, they all have exactly the same type requirements. Possibly with one exception that we documented in the technical report, which would be that sort may require copy construction or copy semantics. But that's beside the point. We can actually just write all these requirements as sortable I or sortable IR if you're sorting with respect to some relation. The idea is that we can actually dramatically simplify the requirements for all of these algorithms by just giving the one concept that constrains the entire family. And all of these algorithms have exactly those requirements, possibly with stronger iterator requirements than forward iterator. So yeah, sortable has a forward iterator requirement, like push heap has a random access iterator requirement. So we can strengthen those and then just reissue the same sorting requirements for the algorithm. I wish I had an example of that. And I wish void were not capitalized. That's unfortunate. It's a new type. So one of the goals is syntactic simplification. We don't like writing long sets of requirements for these algorithms, and so we haven't. If you go through and look at the technical report from N3351, I don't think we have any occurrences of type names. Like the type name keyword is not used in a single signature. There's not a single : used in any signature that we have for the algorithms. It doesn't look like template metaprogramming, and we think that's a big win here. Thank you. We're trying to sometimes eliminate all uses of the word requires. We think that writing things like the first sort algorithm is kind of nicer than writing the second one, just because it tends to be a little bit more terse. It can communicate requirements a little bit more effectively in a lot of cases, I think. And we haven't introduced the notion of a concept map. And I know that a lot of people were very fond of concept maps. They were a very powerful feature. But when we revisited the problem and looked at constraining the STL, we discovered that we didn't have to introduce this really powerful, complicated language feature just to get what we actually wanted, which was concepts describing and constraining the STL. So we don't have them. They may come back. That's not been decided yet. This is still very early work. There are a couple problems left in the specification. I think merge algorithms are a great example of these. So this is merge and all of the set union, set different, set intersection algorithms. They all have this same mergeable requirement. And it turns out that when you write these out, you get tired of typing all of this input iterator 1, input iterator I2, weakly incrementable out. You get tired of writing this over and over and over again. They all have the same requirements. We should be able to use a concept to introduce these type names in a constrained way. And the syntax that we have right now is not fantastic. It's purely speculative at this point. So we could possibly use a concept like a macro to introduce the type names associated with that template. And this will automatically introduce the type names and constrain them exactly like you have above. It doesn't really fit with the rest of the language, so I'm not terribly thrilled about this particular syntax. Still working on that one. Inner product is still a problem. I know we gave this example earlier, specifically because it's a problem. It turns out that if you actually fix the value types of these two iterators and t here, then you can write pretty compact requirements on it. The algorithm requires a semi-ring, which is pretty much you have plus and multiplication, or addition multiplication. The problem is that we tend to generalize our algorithms to the point where we like having heterogeneous arguments. The value types of the two iterators and t may differ in some respects. So you could have a vector of ints, a vector of shorts, and t being a double. And the compiler will happily accept this and probably do exactly what you think it will, which would give you the inner product with everything properly converted to doubles on the way out. Unfortunately, when you try to write the requirements for that, you end up with something like the bottom one, which is not a whole lot better than what we had before. It still restates the implementation. It exposes a little bit too much about the actual algorithm and doesn't express the intent of the algorithm as much as we'd like. Trying to solve this problem has actually been not easy. I still have no good answer to this one. It is headache-inducing. Spending 2 days thinking about the requirements of one algorithm is not fun. OK, so what are we doing now? Well, the concepts TR we actually finished. That's published. Bjarne mentioned it. I've mentioned it a couple of times. We're continuing to build the work out. So I'm starting to look at the numeric library. I'm still looking at the numeric library. Moving on to containers and ranges. Actually, we cut the numeric library out of the technical report. That was probably another 20 pages. But we kicked it out specifically because of inner product. We're still working on the language design. There are a lot of features that we haven't talked about. So things like separate checking, I didn't touch on that at all. That's definitely still going to be there. We're just working out the details on it. Still no concept maps, just really haven't found a great need for them. We're still going to continue experimenting with libraries, and I'll give you a good example of how that's working right now, or pretty soon here. Bjarne's book, the C++ Programming Language 4, will also address a lot of these issues, but in the context of the current version of C++, not speculating about a language feature. And then Gabriel Dos Reyes is working on type theoretical aspects of concepts and their relation to type classes, or will be at some point in the future, we hope. So some references. I forgot to put a link to that paper there. In 3351, I think if you Google it, or sorry, Bing, it becomes the, I think it's the first hit already, strangely. Or it was for me when I looked it up not too long ago. Concept Clang is work being done by Laurice Vuffo and Marcin Zalewski at Indiana University. They're actually implementing the grammar and language mechanics we decided from the technical report. Laurice thinks she'll have a release done hopefully soon. I think she said maybe as early as next week, but certainly not any longer than a couple of months, I hope. And that is the webpage to go investigate and see the status of that. And then there's Origin. Origin is my library. It's an experimental collection of C++ generic libraries. All of the concepts that went into the TR were prototyped using C++ 11. for this library. And I've been sort of building this out to cover the standard template library. So everything that we actually have in the technical report is now being checked against actual library implementations. And since we got away from C++11, we'll go back to it. This is actual live code from Origin, compiles with the latest and greatest GCC because they have the most C++11 support. So it's actually compiling out against GCC out of Subversion, which is, I think, now 4.7. But this is what the standard count looks like. Disregard the O in front. That's so I don't get namespace collisions with the standard library. So we can have a concept here called search, and we just static assert that. So this actually says the iterator type I must be searchable for some value type T. The requirements of search are input iterator and equality comparable. I'll show you what it looks like in a second. The assertion is readable range. Basically says I have to be able to go from first to last, and dereferencing from each of these iterators must be valid. That doesn't actually do anything at the moment, but it will be specialized for forward iterators, so it actually will do a runtime check if the requirements are met. The implementation is as you would think it is. This is what the search concept looks like. It's just a const expr function. Gone are type traits. It's a const expr function that just evaluates other const expr functions. Input iterator is actually just exactly like this, although slightly more complicated. Equality comparable. We actually have two overloads of equality comparable. Here, this is the cross-type equality comparable, so we can actually compare A and B of different types, heterogeneous arguments. This is the tip of a very large iceberg. If you're really interested to see how this works, and it does work, you are more than free to investigate, but there is a lot of substitution failure magic going on behind the scenes to actually evaluate these concepts. Just to be clear, this is actually C++11 code. You can download it and compile it if you have the right compiler. It's perfectly valid, assuming I haven't broken something in the last 2 days. We've experimented with concept design. Our goal was to actually find concepts that made sense. Were easy to write, were easy to read, represented abstract ideas instead of implementation details. These principles actually lead to a much simplified specification of requirements for the STL. So what's left to do is actually all of the dirty work. We have to go through and figure out what the language actually does, how the mechanics of it work, how it's going to interact with all the other features in C++11, how you constrain class templates, which wasn't addressed at all in this talk or in the technical report, still a big open issue. We're still building out. We're looking for concepts in other domains. So the numeric library is a great example. We're working with Peter Gottschling to build up a set of algebraic concepts to accurately constrain interesting numeric libraries like linear algebra for linear algebra applications. Refining the concepts, that doesn't necessarily mean refining as in the C++OX sense of refinement, but making sure that they actually make sense. Language support mechanisms, and improving the specification, apparently. So we have a lot left to do. Again, this is very early work, but I think we made a lot of interesting headway, and I think we actually got very good results out of this work. I'm looking forward to seeing what happens next. So, are there any questions?
I'd like one comment before we do this. So we had 1 hour. We went from philosophy to concrete running code that has actually passed about 9,000 test cases. So this is very concrete philosophy, but it's still preliminary work.
There's one back there. How many people likes to write for your class, which is, say, less comparable or maybe equal comparable, to dump 4 or 5 functions, which is essentially inverses? You switch parameters, change braces. And there used to be this real ops namespace, which a lot of people recommend not to use because there is no way to safely use it. And some people resort to macros to fix this problem. And by looking at your axioms, it seemed like it is the way to actually hint that, hey, I want actually this thing to be, generate for me not equal, if you have an equal, or all of other flavors of less equal, greater than equal, etc. And actually, maybe the bigger question is, what is the future of real ops? Maybe axioms is that future.
Well, so one of the reasons we decided not to, well, I don't think it was one of the reasons we decided not to pursue that as an option, but it turns out that you don't really need to provide these those algorithms, these default overloads in the context of a concept, because you can actually just stick a constrained template in the global namespace, and the standard overload mechanisms will pick the right overload if you've defined one, or supply one automatically for you. So the fact that we can actually constrain templates gives us a lot more power to actually put things in the global namespace and not necessarily worry about interesting overload collisions.
In other words, Origin does that. If you use Origin, you have equals but not equals. It will generate it for you if it can, given the constraints.
Origin could do that.
This has been.
Well, it did in a previous version.
Okay, it did last time I did it.
I took that out.
But basically, we have managed to separate a lot of things out. If you've seen the previous work, this is a radical simplification in many ways, close to an order of magnitude in places. And one of the ways it's been done is not to try and do everything inside the concepts.
So make one from Twitter, because we haven't been doing
Yeah.
that much.
Do we just read the one right
I'll
here?
read it. I'm aware of the trade-offs between concepts and Andre's template constraints, but what's your take of it? I'm not quite aware of the trade-offs. In both cases, you depend critically on predicates, on types and values, and that's the same. Our approach takes semantics into account and is a highly structured facility, whereas if is, among other things, a mechanism for random hacking. Now, whether the one or the other is better or simpler, I don't quite know. I have not had enough time to think about the ifs and static ifs and how the code will look from it and what uses or misuses there can be. So I would rather not have a firm opinion about this, not yet. Give it time to sink in. We have rushed to decisions too soon. We have two things. They both work for some things, but let's just take a time and think.
Go for it.
On one of the last slides, you showed that we can emulate concepts with static assert, and the Clang folks showed that we can get useful errors from the compiler. Why do we need to extend the language while we could maybe already have that?
In this particular case, because the static assert sits in the definition and we want the checking to be on the declarations, we want the checking to happen at the first use, not at the time where you instantiate and see the definition. That's the most important part of the answer to your question.
Right, and one of the issues, even though we have a static assert and we can guard these, when you instantiate and you fail, you're still going to get a pretty deep instantiation stack, so you still get the template barf. But you can customize the errors to say something a little more meaningful, like, I is not an input iterator or something along those lines. But you still get the stack.
We're running out of time unless you have a really fast question. Then a fast answer.
I saw that Alex Stepanov was at the meetings. Could you say briefly what his role was and has been and will continue to be in this effort?
Let's see, he's a dictator for life in this concept. He pushes very, very hard for one particular view of things, which is very good. He has been thinking about it for a couple of decades. His views has refined over the years. They are definitely different from what they were 5 years ago. He led the meeting, he set the agenda, and basically cut the discussion when we were becoming long-winded. Somebody has to do that in a group of, 14, 15 people at a lot of times. And he focused on algorithms. There's been a lot of work on concepts that's been focused on classes and such. This was clearly focused on algorithms, and it was clearly focused on mathematical soundness. In particular, he was worried a lot about hackish uses of concepts. For instance, when you have non-homogeneous elements like operations that mixes, doubles, and ints, how do you know you get a mathematical meaningful operation? How do you mean you can state axioms for it? And at some point he bore down on him and says, Leibniz disagrees with you. Actually, I won that one. But I hadn't expected that. But he was really into classical mathematics and trying to make sure that this was sound. That was his major role. And he's the driver. He's the one that gathered the group of people together. Without him, nothing would have happened.
Thank you, guys.